This lab involves learning about three-dimensional plotting and graphing things that appear to be three-dimensional. And I'll try to talk you through it. The first thing you need to do is change your preferences so that the angles are directed degrees, and under the text tab make sure it doesn't show labels automatically when new points are measured. Then you make a circle that's 2 centimeters in radius. You put a point on it and you measure an angle. That's so you make a slider. We'll call the angle theta. And you can see that when I move the point around, the value of the angle changes. So I can set theta to whatever I want. Then I want to make some action buttons. First of all, an action button that will set theta to 0. And second of all, an action button that will make theta run around and around the circle, animated. Now it's going to be very useful to have sliders like this since we're dealing with a lot of rotation today. So I'm going to select everything here and create a tool that automatically constructs a slider. I'll call it Make Theta. Now this is a lab about rendering things in 3D. So how do we do that? Well, we imagine rotating them about various axes, and then we draw a two-dimensional projection of the 3D object as it's rotated. So we want to study rotations very carefully. Now, if I have a point, say 3, 4, and I want to rotate it about the origin, what happens? Here's how we can use our theta angle slider to construct a rotation of this point 3, 4. Now we had to rotate it about the origin. We had to select a point to rotate it about. So the origin is going to be one of the inputs in our tool, and this tool will be called Rotate About Origin. Now we want it to always rotate by theta and always about the origin, so we make origin and theta assumed values. And now let's see if our Rotate About Origin tool actually works. First we make new theta. We have to label the point origin because it's an assumed point. And now we're going to try it out on a bunch of points that are given to you to see what the secret picture is that's going to emerge. First we create all of these mysterious numbers. And then we use the Rotate About Origin tool, and we click on them in pairs that are given, each pair representing an xy. And every time we click on a pair, we get an x prime, y prime. And each x prime, y prime pair represents the coordinates of the rotated version of the point that corresponds to the two values that were clicked on. Now I have a whole bunch of points. Now I want to plot them. Now if I select 2 points and say plot as xy, I get that point appearing. But to make this easier, let's make a tool that automatically plots as xy. So that all we have to do is click on these points and the new point will get plotted. And I could just click down the list. It's much faster. And we see a beautiful picture emerging. That's all the rotated points. So when I use the buttons that reset and animate theta, I can see that they affect all those points. Now, what we didn't like about this Make Theta tool is that it depends on origin. So there's an exercise in the lab where you figure out mathematically what are the coordinates of x prime and y prime. And you can simply do that calculation, and therefore your script won't depend on the origin, and you get an improved version of the Rotate About Origin tool, which I call Rotate About Origin Improved. Now the only assumed object there is theta. Now we'll test it out. First we'll take these values again, copy them, and paste them onto our new page. We need a value of theta, so we use the Make Theta tool. And then we go to Rotate About Origin Improved, and we click on these points in turn. Same pairs we were using before. So this is the exact same process we used before, and it should give us the exact same result. The only difference is that this time we didn't have to relabel the origin point origin. So it's a little simpler. And there's again that lovely picture, and again it responds to the buttons that control theta. Now we go to a new page again, and we want to start thinking in 3 dimensions. So here's coordinates of a 3-dimensional point, 2, -3, 5. If I rotate x and y about the origin in a 2-dimensional system, then it's the same thing as rotating as x, y, z about the z-axis. So I simply make a tool that rotates x and y about the origin and leaves z unchanged. For example, if I rotate 3, 4, 5 about the z-axis, I get some x prime, some y prime, and 5. Now I want to rotate about, now I figured out how to rotate about the z-axis. It's easy to figure out from that how to rotate about the x-axis and the y-axis. So let's make up 3 angles where alpha will be the amount we rotate about the x-axis, beta will be the amount we rotate about the y-axis, and gamma will be the amount we rotate about the z-axis. So first we want to be able to make alpha, beta, and gamma on every page we go to. Now we go to rotate about z-axis, and we change it so that instead of automatically matching the angle theta, it automatically matches the angle gamma. Now I make up an x, y, and a z. I know that I can rotate this about the z-axis, but if I choose the points in a different order, y, z, x, just a permutation, a cyclic permutation of x, y, and z, then it's got to change it from rotating it about the z-axis to rotating it about the x-axis. I rename the output points correspondingly, and I make a new tool called Rotate About the x-axis. And then just to make it work with alpha, I changed the input from gamma to alpha. So I didn't have to really make a new tool. Once I had a tool that rotated about the z-axis, I kind of automatically got a tool that rotates about the x-axis. And it works perfectly. It gave me x prime, y prime, and z prime when I used it just now. We're going to try the same trick to rotate about the y-axis. Okay, instead of choosing in the order x, y, z, or y, z, x, I'm going to use z, x, y, and again rename the output. So now we label this rotate about y-axis first try, because you'll see it actually doesn't work that well. The problem is that z is created before x and y. So let me grab these points. If I run this tool on these points, I get y prime, then z prime, then x prime. That's going to be a nuisance. I want the tool to put them in order. So I use this clever trick. I recalculate y prime so that it depends on x prime, and I calculate z prime so that it depends on y prime. And now we make a new rotate about y-axis tool, and you see that they come in the right order. X prime, y prime, z prime. And now we have the tools for rotating about any axis by the angles alpha, beta, and gamma. Test it by taking some point 3, 4, 5. Now first we rotate 3, 4, 5 about the x-axis. by alpha, then we rotated about the y-axis by beta, then we rotated about the z-axis by gamma. And we look at the results. We plot just the x and the y pairs, and we see what happens when I run these angles. Now this is a point revolving about the x-axis. Of course, we're just looking at a projection of it. So to us it looks like it's going back and forth. Here's a point revolving about the y-axis. Now we're going to try to use some more interesting points, the 8 corners of a cube. So let's say the cube corners are at coordinates positive or negative 1. And I'm going to take all 8 coordinates of the cube and revolve them by an angle alpha about the x-axis. And then I'm going to take the resulting points and revolve those by the angle beta about the y-axis. So here are all my doubly rotated points, and now I'll take all of those and I'll revolve them by the angle gamma about the z-axis. So now I have the points corresponding to the corners of a cube rotated about the x and then the y and then the z-axis. Now we'll plot them. I'm just clicking on the x prime and the y prime of each group, and the 8 points I get should be the points of a cube. So let's try rotating them about and see if it starts looking like a cube. And it does. Once you can visualize the cube, you put in the line segments. And we've constructed an illusion of a 3D object just by simulating rotations and projecting a 3D object onto the plane by ignoring the z prime component. So it's fun to play with the cube. We can make it bigger. We can hide all of the non-essential things. All the text is hidden. I can hide all the points and make the cube turn about in strange ways. What I want to do next is put a stick figure embedded inside the cube, just to show that this is even more powerful. So again, there's a set of prescribed mystery points that were worked out beforehand to be the various points on the stick figure. We're going to take these points and first rotate them about the x-axis, then rotate them about the y-axis, and then rotate them about the z-axis so that they rotate exactly with the cube. Okay, we finished the x-axis, now I'm rotating them about the y-axis. Finish that, hide all the things that I don't need, and take the rest of the points and rotate them about the z-axis. Then I plot the x and y, or x prime and y prime coordinates of each of these to see what the mystery points are that were plotted. Again, I'll hide all the text, and when I rotate it, you immediately get the illusion that those points are inside the cube. It's a little hard at first to see that it's a stick figure, but here's how you connect the dots. Now the 3D illusion really shows you how the stick figure is standing within the cube. It's very powerful. But he's missing a head. How do you give him a head? Well, I figured out the equation of the circle that would be his head. The circle is the circle lying in the xy plane at a center 0, 0.8, 0, and radius is 0.2. So I simply construct that circle, construct a point on that circle, and assume that the z coordinate of the corresponding point in 3 dimensions is 0, so that it's in the xy plane. Now if I take these 3 values and rotate them the same way the cube is rotated, first about the x-axis, then about the y-axis, and then about the z-axis, I get a rotated point. and the locus of that rotated point is a rotated circle. And that's how I get the head of the stick figure. Okay, we stop all motion. Let's make a new blank page. Now let's think about theta and phi. Theta and phi are described in your write-up. I'm going to rename everything so that we got rid of gamma, we're renaming alpha and beta so they're theta and phi instead. And we make a new tool that just makes two angle sliders, theta and phi. So we make this test point, and the first thing we do is we rotate by an angle phi about the z-axis, and the second thing we do is we rotate by an angle theta about the y-axis. I hide the intermediate points, and I make a tool that does these two rotations. Now I called the inputs T1, T2, and T3. I never called them X, Y, and Z. But you could actually change that in the script. It makes the tool a little easier to use. Now on a new page, we'll test out the tool. Our job here is to stack a bunch of circles, and the circles are going to be parallel to the YZ plane. So we make the only kind of circle we can make, a circle in the XY plane. And we measure the coordinates of a point, but then we pretend instead of XY that we have ZY, so that we have the points on a circle that's sideways. And then the actual X coordinate is the coordinate of this point. And now to visualize a cylinder, I want to make a bunch of circles spaced 1/8 of a unit apart. And I advance it by 1/8 of a unit. That's going to be my next X coordinate. And then I do the theta and phi rotation of that point. I take the locus of it, and then I iterate this image so that we have it stacked up in the X direction. Now I glue this point to the unit point so that the cylinder starts at the correct X value. I'll make the lines easier to see by making them thinner. I'm going to hide the things that I don't care about. And now you can see our cylinder is rotating around. All right, here's what it looks like when theta is 0, so we're viewing it from the top, and this is theta is almost pi over 2, so we're viewing it just a little above. It's a little harder to visualize without the actual axes. So here's a cute way of visualizing the axes. Just put a point on each axis, measure its X and Y coordinate, pretend that each has a Z coordinate of 0, and then rotate them about theta and phi. Plot their rotations, and now this is the rotation of a point on the axis. So if we plot its locus, we see the whole axis. Hide all these points, and you can see it's a little easier to see exactly where on the axis that cylinder is lying, and it's a little easier to interpret what the angle phi means.